Good morning. John, can you hear me?
No, sir.
Hi, John. Good morning.
No, sir. Good morning.
Yep. How are you?
I'm good, sir.
Okay. Okay. I was about to ask you something. Let me see. Yes. Okay. Yeah. I kind of forgot what I want to ask you. Um. Yeah. About the recordings. Were you able to finish all the recordings? Like upload
Yes, sir.
them?
I
Okay.
uploaded. all of the
Okay.
recordings up until the session yesterday.
Okay. Gotcha. So yeah, let's wait for them. Let's wait for them. They will be joining in a few. We'll just be on standby.
Okay, sir.
Hi, Asiba. Welcome to the meeting. Can you hear me, Asiba? Um, if you're trying to say something, you're on mute, Hasiba. Let me see the chat box. Okay. Hasiba says, hi, everyone. I'm outside and in the car. Okay. Thanks for letting me know. Um, let's wait for a couple of minutes and then we'll start with the recap before we proceed to the things that we have for today. Um, I will just listen to you. Okay. Yep, that works. Hi, Grace. Welcome to the meeting.
Hello, sorry I'm late.
Yeah, no worries. Yeah, I think we can start now. So basically, I just want to announce that tomorrow you will not have any lab session because of the Independence Day, and also on Saturday there will be no classes, both lecture and labs. The school designed that so that you can enjoy the long weekend. So yep, we have to finish the topics that we have today. So let's start with a recapitulation of the last session. I hope you can see my screen, right? Can anyone confirm? Grace, can you please confirm if you can see it?
Yes, fancy
Thank-
screen.
Okay, okay. Thank you very much. So, yep, just a quick recap of what we have discussed the last time. We were not able to finish all of the topics under lecture one, so we have to do a catching up. So the last meeting, we have discussed the basic background about statistics, what is its important, or what its importance with data analytics. Why is it important for us to learn? So basically, this is the language of data. So if we want to be master of data, be able to navigate through the methods to how we can manipulate this data for our benefit to uncover potential insights that we can use, we have to know statistics. So we have discussed this different applications of statistics, but if a field or an industry makes use of data, then you can apply statistics with it. So basically, this is a multidisciplinary subject. Okay, and oftentimes there are different terminologies for the same methods. So we have to dig deeper. Okay, they might be calling some methods in classical statistics differently in their field, but they are pertaining to the same method. And we have talked about this different uh, s- subsection, or I should say sections of statistics. So descriptive statistics and inferential statistics. And by now, I should say that you are already familiar with the methods of descriptive statistics. So the measures that you have derived during your Python sessions and your final project, those are under descriptive statistics. So we've already touched that aspect, that section. So when you tried to generate those means, those medians and modes, the percentiles, the quantiles, and standard deviations, you're essentially doing descriptive statistics. Now we are moving towards a more complex topic under the section of inferential statistics. How can we generalize the result taken from a sample for the entirety of the population with some degree of confidence and uh, precision and accuracy? So that's what we try to learn during this section of statistics, and we will be doing that in Python. So you'll be able to further master your Python skills. And we've discussed these different data types, categorical and numerical. Under categorical, we have the nominal ordinal. So basically, for nominal, these are just well names that we associate, or categories, I should say, for identification. So there's no hierarchy. There's no innate difference, innate order between the categories. You can think of gender, ethnicity, and colors. There's no thing that tells that one gender is basically better than the other. One ethnicity is better than the other. So just a way of categorizing things. Um, with the ordinal data, you have an inherent order within your categories. So one category is better than the other in terms of a specific characteristic. So in terms of strength, we know that males are generally stronger than females. In terms of educational levels, we know that um, well you need to spend more time when you want to get higher level of education, right? So there's this natural order in, between those levels. And we had this example, and I think John went over the some of the nuances of this test. So, but what I want you to just pick on this is for every data type, there's a specific method that you can use. So it's not a one size fits all thing. It's not that one method can be used on like any data type. It's not the case. So you should be familiar. Okay, I have this categorical data, and I want to say, see if they are associated with each other. Then you can use chi-square test, right? So by now, I think you're already familiar with it, but in terms of understanding the like the theoretical aspect of it, I think it's something that we should reserve for after we've discussed probability theory, because all of this would be needing the foundational knowledge about probability distributions. So I assure you that will not be needing to go over the maths. It will just be about the concepts and how you would use it. So this is only one way in which you can run chi-square test in Python. There are other packages that you can use. You can even create your own function that will do exactly the same thing. It's completely possible to do that if you're familiar with the manual computation. Okay, but this libraries are readily available for you. So if you want to save time, you can just follow the steps, follow this framework, and you'll be able to get the result. Okay, we've discussed intensively the concept of p-value. We said that it is your risk, right? It pertains to your null hypothesis. So in inferential statistics, there are two hypotheses. First is the null hypothesis, or what we call hypothesis of no difference. Okay, so if you're considering gender and preferences or preference here in this example, then the null hypothesis is there's no association between gender and preference. Okay, that's your null. And then your alternative would be the converse of your null, and that is there is association between gender and preference. Now you'll be using the samples as evidence, okay, and your process will be chi-square test to to see to reveal if there's sufficient evidence to say that the null hypothesis is highly uh, highly likely or less likely. If we observe a statistic or um, evidence to say that the null hypothesis must be incorrect, then we can reject it for the alternative. Okay, we will be finding a sufficient proof to say that okay, with 5% probability of committing mistake, we can reject the null hypothesis in favor of the alternative. So that's what we'll be doing for the rest of the topics under inferential statistics. Okay, again, the concept of p-value is your risk. You can adjust it if there's a concern about anything related to health or life and death situation, then you can make it further less. The standard for it is 1%. But for more, I should say, um, more conservative values, you can further decrease it. But of course, that would be requiring you more evidence, more samples, and a much more extreme statistic in order for you to reject the null in that case. So we'll be talking about that, those nuances about the concept of critical value, the concept of the different statistics, and so on. Okay, and we have discussed this median and interquartile range, which are both under descriptive statistics. However, you can use this if you're dealing with ordinal data. You can use the median as a measure of central tendency, the same way that you use the mean in order to summarize, to have a composite variable or composite value that would summarize the 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 sample or the data that you have in just one value. And then we have the IQR, which is basically a measure of variation. We'll be discussing another measure of variation. So we have now standard deviation. Okay. So the standard deviation is the variability around the mean. But there are flaws with the standard deviation because we know that if we have an outlier, or not even an outlier, if we have large fluctuation of values, okay, not necessarily an outlier, the standard deviation would be very high, and there would be instances that you can't use it. Okay, like for example, if you try to compare the variability of two values that are of different scale, okay, say maybe a better example would be comparing the variability of the prices of toilet paper versus the variability of prices of cars. If you try to use the standard deviation there, then you would always observe that the standard deviation for the prices of cars would be significantly higher, and there's like uh, uh, um there would be something wrong if you try to compare them, because all the time the price of the cars would be um significantly higher as compared to the prices of the toilet paper. So there's another measure called coefficient of variation that uses um, the the internal deviation relative to its mean. So the variation would be represented in terms of percentage relative to their means. So we can eliminate that problem of having different magnitudes when we compare variations, such as that example of comparing the variation of toilet paper versus a variation of um, the prices of cars. Okay, because there's no way, there's no intuitive way that you'll be able to compare the variations in the prices of those two categories only through the standard deviation. Okay, there's no way for you to do that. So there has to be another way. And we've also discussed numerical data. We've discussed interval data and ratio. And the major difference between the two is that the interval data has no um, real zero, right? For example, degrees Celsius and degrees Fahrenheit um, both have this different values associated with a zero. However, if you argue, okay, Jeff Kelvin has an absolute zero, 0 degrees means zero. There's no temperature at all, and it's completely intuitive to say that 20 degrees Kelvin is twice as hot as compared to 10 degrees Kelvin. So if you have an absolute zero, you can do that type of referencing. Then you can argue that temperature in Kelvin is of a ratio data, not on uh, interval one. Okay, so make sure that you always verify that, because while the interval and ratio data they're somehow comparable, the interpretation, especially if you use them in a statistical model, would be different. Like imagine you used temperature measured in terms of Kelvin in your regression model, and what does it mean to have like 0 degrees Kelvin is not even, well, theoretically it's possible, but um, realistically speaking, it won't be, because if you say that something is of like that cold, then the universe would collapse to that. Remember thermodynamics. The temperature, the hot temperature moves to the colder regions. So the universe would collapse to that. So theoretically, while it is possible, it's not realistic. Okay, only exists in theory. So, what are the key differences? Measurement levels and statistical analysis. So, am I saying that you can do categorical analysis such as chi-square statistics with either ratio or interval? The answer is yes. You can still do it. How? Remember, remember the discussion that we had about statistical power. I said that from racial level, you can degrade it, okay, to ordinal level by creating these categories and associating characteristics to them, like age, right? We can associate, okay, um, maybe 13 to 19 as teenagers, then 20 to 30 as young professional, and 31 to 40 as like or 50 as middle age, so something like that. So from being a racial level, we moved it to an interval by creating those ranges, and after that we associate characteristic and convert it to an ordinal one. So you can do that. That's why the racial level has the highest statistical power, because you can do so many things with it. Okay, so in your data collection, it's better if you can represent it in racial level, so that in the future, if you want to do categorical data analysis for whatever reason, then you can just convert. Okay, you can just transform that variable into a much lower. I should not say much lower, but on a different measurement level. Okay, one with a lower statistical power. And we had this example. This is through NumPy. So I think Grace told me that she was expecting more of NumPy in the following sessions, because I think that would be very useful in the future. So yes, in the succeeding topics, there will be more NumPys, because we will be applying so many computations with our data, generating this different statistics. So as you can see in here, we just applied the mean and just generated the standard deviation. That's basically it. Now, moving forward, so this is something that I think John already introduced to you. Correlation. So what is the difference between the terms correlation and association? Because oftentimes people use them interchangeably, like they treat them as synonymous. In reality, they are not. Association is a generic type of relationship. Okay, when you speak of association, it's generic. However, when you say correlation, you're particularly um, pertaining to linear relationship. So the linear relationship could be direct or indirect. Direct meaning as x increases, y also increases. If indirect, x increases, then y decreases, and the other way around. So those are the different types of linear relationship that we generally call as correlation. Okay, so correlation is a specific term used for that type of relationship. And if, say, we establish a relationship between at least two variables, x and y, we can somehow do predictions using linear regression. So is linear regression only used for prediction? No. You can also do um, other things with it, like understanding the impact of one variable on the. So you can somehow quantify the effect of your x to your y. Okay, how significant is it, or how strong it is? So you can use linear regression with that. And regression is, in data science, a specific term used when your target variable or your y variable is numeric. Okay, remember that when you might argue, Jeff, there's this called logistic regression that has a target variable of a categorical nature. But in reality, in logistic regression, you are basically modeling probabilities there. So under the hood, what you're modeling is really numbers, probabilities. Okay, so that's why it's also called regression. So if your target variable is categorical, like in an AI system, you're trying to predict whether an animal that's been captured by your camera is either an elephant or a monkey or a cat. So you're trying to develop that model, then that is called a classification model. Okay, so in data science, you have a regression for your when your y is numeric, and you have this classification model that uses also the same idea, but you're basically modeling probabilities there. What is the probability that what you have captured is a monkey? okay, or what the camera uh, saw is a monkey or an elephant, okay. We can model that, okay. That's under computer vision. So I have here an example of correlation analysis and also linear regression. So one of the requirements of linear regression is that you should have variables that are correlated with each other. And by the way, I should highlight this. Correlation doesn't imply what? Grace, Hasiba. Correlation doesn't imply
Sorry,
causation.
can you repeat that? This correlation?
Doesn't imply causation.
Oh yeah, it does not, right?
Yeah, yeah.
It,
It's
yeah.
it's an important phrase, and even smart people commit that mistake before. A Harvard professor committed that mistake, that he interpreted correlation as causation. So, for example, it so happened that a country's GDP increased by 10%, and its COVID cases increased by as much. There could be high correlation with that, but you cannot say that the reason why COVID cases increase is because of the increase in GDP or the other way around. You cannot say that. So in most cases, you can imply causation, you can conclude causation if you have a controlled environment. You can do that through experiments. You can do causal inference through that because in a controlled setup, you are trying to eliminate those external variables that could be affecting your result. You can be sure that the reason why the reason for the decrease or increase in whatever you're measuring is because of the treatment that you have applied and not because of external factors. Okay, so that's one best way of identifying causation and measuring it in a controlled environment, an experimental one where you have um, blindings and randomizations. Okay, but there are advanced methods that we can also use in order to do causal inferences, even with an observed um, variable, but it's outside the coverage of our course. Now, what I'm doing here, let me go through the codes because I want this codes to be as clear as possible for you. So we have imported the necessary libraries here. So we have matplotlib. Jeff, this is something new. Matplotlib. Um, this is the typical library used for plotting in Python for data analysis and data science. So we have a dedicated section. If you have seen the topics that have lined up for this statistics section, we have this specific discussion about matplotlib. How can we do um, nice plots, visualizations from our data using Python? So we'll be using three packages for that: matplotlib, um, plotly, and seaborn. In the past, I've used mostly matplotlib and seaborn. Plotly is more on the interactive, but when you're publishing papers, it doesn't need to be, well, it should not be interactive because there will be like in a what do you call that, in a journal. So it does it should not be interactive in a sense that you can have cursors in there. You can hover to the dots and the elements of the charts, and there will be this information, additional information for you. And as usual, we'll be using sci-fi stats. So as much as possible, I want to use a single library for all of the topics here in statistics for the methods, so that you will not be confused. Because if you try to use other libraries, um, it might confuse you because this is, I think, the first time that you'll be seeing this well, of course, this library. So moving on, so we are creating sample data set here. We have temperature, we have ice cream sales. So both are what of data structure, Grace and Asiba? What is the data structure of both of this? List. Okay, both of them are lists. So this is list, this is a list. Okay, and now um, it doesn't have to be in a data frame format. But if it's on a data frame format, what we can do is, okay, you can extract that, or you can do not specifically extracting, but accessing through the square brackets, right? If it's in a case such as that, it's on a data frame, you can just extract the columns through the square brackets, and therefore you will have a sort of series or a list type of object. And now you can apply, once you have that, at least two variables, you can do correlation. So that is, first, you'll be generating this correlation coefficient. So this correlation coefficient pertains to Pearson correlation coefficient. Okay, let me go back again to Wikipedia. Again, don't hate me. Don't hate me because I'm using Wikipedia. Um, we'll be able to spot any error if there's any. So don't worry. Okay. I just think that Wikipedia is very efficient in providing a good discussion. So I just want to show you the formula. So this is the formula of the correlation coefficient in a perspective of a random variable. Okay, so the correlation coefficient is just the covariance between your x and y random variables divided by its standard deviations. Okay, now in the applied version you have this. Okay, so it looks complex, but if you look at it carefully, it's not really difficult at all. But again, you don't have to memorize the formula. I think it's a bad practice that teachers require their students to do memorization of formula. It doesn't make sense. Imagine looking at this and spending your brain power memorizing this stuff. Okay, so I think it's more necessary to have, like, to focus more on the understanding. So looking at this, let me pick up my Epic pen. I want to highlight some things here. So the first question we have to ask ourselves is, okay, how many variables do we have here? So we have two. We have x and the y variable. Okay, and then what is this n? N is the number of observations. So if you have like 100 data points, that n would be 100. Okay, and then the summation right here, okay, it just tells us that it will be summing up the products of x and y. So if you have, say, an x value of 30 and a y value of 40 for the first observation for the first pair, and you have in the other 40 and then 50, you'll first get this the product of the first observation, 30 times 40, plus the product of the next. So that's basically what you're trying to do here. When you apply the sigma notation for the product, it's just telling you, okay, get the product, add it to the next. How do we know that? We have the I in here. So the xi yi in there. This has to be a bigger y. So that would be from the first observation where I is equal to 1 up to n. N is the last observation. So that is basically, okay, I get the product of the first pair plus the product of the second pair, and so on. So that's basically what's happening in here up to the last pair. Okay, so basically, um, that would form your part of your numerator. Okay, and then this is just easy total values of x, right? It's just the total x plus 1, x sub 1 plus x sub 2 plus x sub 3 up to x sub n. And then similar with y. And then you multiply the total together. Okay? That would be your numerator, this entire thing, this expression. And then at the bottom, okay, what you have is the square root of the squares. So that is the square of the total, okay, multiplied to the total number of observation minus the square of the sum of each x. So this is different, okay? These two are different, okay? So basically here you're summing each of the values, right? Here sorry, let me say it again. Here you're squaring, okay? You're squaring each value and getting the sum for each, okay? So if you have like x1, x2, and so on, for this part right here, you'll just square it first. Get the square of that, get the square of that, and just add them together. That's what you have on this part. Oh, how can I change that? Okay. Now on the second one is you get first the sum, which is basically what you have at the top, this summation of xi here. So that's the total x. Get the sum of everything, of every x values, and then you square that. So that's the difference between this sum of x squared, in which you are summing all of the squares, and then here, after getting the sum of all the x values, you then square it. Okay? Do you follow, guys? Of course, you don't need to do that manually, right? You don't have to do that manually. You'll be using software. I will not punish you by assigning manual computation that you have to do. There's no sense to doing that, because imagine if you're trying to analyze millions of data points, then it would take you forever to do that, right? So that's the same here on the other side, but in this part, you'll be doing it for y, and just get the product of the resulting values. And then you'll have the correlation coefficient. But you don't have to go to those things, because the good thing is Python makes it easy for us. Yep. So simply um okay. Now by simply applying this core coef, this function from NumPy, okay, you'll be able to do that computation in a second, maybe faster, okay? And when we do that, it will give you a value from -1 to 1. So correlation coefficients, the values could be -1 if they are perfectly having indirect relationship, or +1 if they have a perfect direct relationship. Of course, in nature, you can rarely observe that. But can you think of two variables that would give you a perfect correlation? A correlation of 1. Meaning knowing the value of x would give you the actual value of y. That's what we mean. And if you plot it, this would look like that relationship would look like this: a perfect straight line. Can you think of one pair of variable that would give you that? Anyone? Okay, let me provide an answer to that. Temperature in Celsius and in Fahrenheit. You just need a conversion factor, right? That type of relationship is not a statistical one. Okay? That type of relationship is called a functional one. There are two types of relationships, guys. Functional relationship and statistical relationship. In functional relationship, the R value is always one. And we don't care about those types of variables because it's just a conversion of one measure to the other. Okay? What we're after with are relationships called statistical relationship. Okay? There's a somewhat um, randomness included in the relationship. If you think of x being height and y being weight, okay, we know that they have direct relationship. As height increases, so that's your weight, but it's not perfect. There are people that um, if you look at the population, it's not the case that if you have 171 centimeter, you have equivalent like always 85 kilograms, something like that. No, there's some degree of variability, right? But we could see if we plot that it looks something like this. It's not perfect, but you would see the trend that from lower values of y, you observe lower values of x. Higher values of y, you would observe higher values of x. So there's a direct relationship within height and weight, right? So those are types of relationships that we're after with, what we call statistical relationship. Just for a minute. There's something wrong with my ace. Okay. Do you follow, guys? We're able to follow that idea about functional and statistical relationships. Maybe it would be better if you have a visual. Let me show you this. It's a material from Pennsylvania State University that I'm using when I teach statistical modeling, and this is a this is a good visualization of the two types of relationships that I just shared you. So this is a functional relationship, a deterministic one, right? It's just a conversion from one degree, from one measure to the other. I wonder if functional should be the correct. I think deterministic should be the proper name for this kind of relationship. And then you have a statistical one right here. You can see the trend, but it's not perfect, right? So we're after with this. We're trying to understand this, the tendencies with the data, with the variables, and so this is skin cancer mortality versus state latitude. So we see this pattern right here. The higher the value of the latitude, the lower the mortality from skin cancer. So it's we cannot say at this point that um, the lower latitude value causes the skin cancer. But we're observing that pattern, so it needs more investigation to conclude that whatever reason, whatever factor that is affecting skin mortality has something to do with latitude. Um, we need further investigation if we want to conclude that. But knowing this pattern, seeing this pattern would allow us to have a justification of doing that, a further investigation. So I'll be giving you this link. This is a nice material, and there are so many good materials in online Pennsylvania State that you can use. I I I, I highly recommend this materials. They're easy to follow. They have tons of good examples. Okay, and I'll be using some of them during the discussion about regression analysis. I've been using that for like 5 years already now, so I've been um, very used to the materials. Now, moving back here, I don't need this anymore. Yeah. So if we run this, what do we expect to see? Let me open my Colab. So don't worry, you'll have a copy of um this codes that you're seeing at your screen so that you can practice it during lab. I just want to show you what you would see if we run this thing. Um, okay, I have it in here. Now I only want the part that is for huh, correlation. Okay. So basically, again, the result of this should be a value that is between -1 and +1 included. Okay, inclusive. So we have a value of 99.9926, which is almost 1. Okay, so the relationship, the correlation between temperature and ice cream is positive. That's one thing that we can um we can deduce. This value is positive. So when a correlation is positive, it means that you have a direct relationship. As the temperature increases, ice cream sales increases. Can we conclude causation here? Can we say that the increase in temperature causes the sale of the ice cream? It's intuitive, right? It's intuitive to say that because the hotter the weather is, you will crave more into food such as ice cream that cools down the body, right? So it's intuitive to say that. Um, so this is an example of a strong positive relationship. Okay, but again, you cannot just conclude that this is causation in in nature. Okay. Um, Now, after we have verified that there's correlation between our x and y, we can now proceed to regression analysis. So with regression analysis, let me go through this. We'll be using the same library, SciFi Stats, and there's this function there that would allow us to do linear regression called linregress. And basically, what we're trying to do with linear regression is uh, first, we want to quantify the effect of your x variable, your predictor, to your y variable, your target. And aside from that, you can identify if that effect is significant. When we say significant, we're pertaining to mm, did that effect happen by chance alone? Okay. If it's significant, then we can say that we have sufficient evidence to conclude that it did not happen by chance alone. The probability that um, your actual effect is 0 is very low. Okay. Now, it's just basically following this format right here. So you have 5 parameters here. You have the slope coefficient. Do you remember the equation of the line, guys? Y is equal to mx plus b. Do you remember that?
Yes.
So yeah, this equation of the line, this m is actually um this m right here is the slope coefficient, right? So I wonder how can I see that AI recommendation again. Anyway, so your m is the slope coefficient. So what do we observe if we have a positive slope? you have a thing such as this, right? You have like a higher rise than a lower, than a longer run, right? Run than rise. So if it's positive, then you would observe that lower values of y is associated to lower values of x, and higher values of y are associated with higher values of x. So we observe this kind of line. So it's not, well, typically it's not like that. The reason why it's almost perfect is because we have a correlation of almost 1, 0.9926. So in most cases, you can observe a correlation or a regression line such as this. It's always a straight line for linear regression. Okay, unless we consider like a polynomial version, that's the time that we'll be exploring a non-linear case. But let's reserve that for some discussion for some time. So that's what's happening here. So that m in your equation of the line is for the slope, and then the b is what? What do we call b in the equation of the line? Okay,
The y-intercept.
that's the intercept, right? So there's a specific use for the intercept in regression analysis. So basically, the intercept tells us that if you disregard the effect of the x variable, you will have an average b. So for example, here, if we disregard the value of or the effect of temperature, did I assign it correctly? Yeah. If we disregard the temperature, then we have a negative 13, which doesn't make sense, right? Um, because it- again, this is Celsius. Um, that's another thing because this is off an interval scale, right? So our regression window for this particular data set is just between 20 degrees Celsius and until 27. So that's where the values make sense to our model. We cannot go over that unless if we want to do that, then we need to have like a much larger range of values. But in this case, it doesn't make to just interpret the intercept, right? And just tell that okay, the ice cream scale sales would be negative if we disregard completely the effect of temperature. It doesn't make sense in this particular data set that we have. Okay, now as a whole, how do we interpret this? So basically, this regression model gives us y, which is ice cream sales, ice cream, ice cream. Where did it come from? Ice cream sales. I assume that this is in US dollars, right? Um, would be equal to 7.074. Just make it 75 times temperature Celsius minus 13.84 844. Okay, so how do we interpret this? So basically this means that every unit increase in temperature, every unit increase or 1 degree increase in Celsius correspond to an increase of $7.075 to your ice cream sale. So temperature has a positive impact, about $7. Okay, an increase in 1 degree Celsius correspond to in average $7 of added sales. Do you follow? Do you follow
Yeah.
that? Yeah. So it's intuitive, right? It's intuitive to get a positive slope coefficient because we know, again, as the temperature rises, then more people would be inclined to buying ice cream. So it's intuitive. There are some times, again, I think I've introduced to you that before. There will be times that people would do statistical modeling such as this using regression analysis, and all of a sudden the result is counterintuitive. There are tons of reasons for that. I'm not saying that it automatically the analysis is flawed. No, it could be that there's some error in the data set. There's some error in like the data pre-processing step, or in the measurement. Okay, in the measurement itself. So when you encounter things such as that, the first reaction should be, okay, have you validated your data? Have you double checked on it? If there's nothing wrong with it, then how did you measure a variable? And lastly, it could be that there are underlying factors that we failed to consider in our model that it 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 resulted to that kind of result. Okay, so those are the things that you have to consider whenever you check the the model, because oftentimes the model will not be realistic and it would be counterintuitive. Intuitive. Okay, but there are just cases like that. Um, I've already encountered them before, and unfortunately, they were presented even to the higher um higher people in the organization, in my previous organization. But uh, you'll just have to tell the team to just go over data again, make sure that you did not commit any mistakes in the pre-processing stage, and reevaluate the processes that you have done. Anyway, going back here, what are the things that I want to highlight here? Okay, so this gives us a basically the effect, right, to the ice cream sales of every unit increase in the temperature. Now you see here an R squared value. So the R squared here is a measure of how good the model is. It's just one way. It's just one goodness of fit measure, the way we call it in statistics. So this means that 98 or almost 99% of the variability of the prices of ice cream can be explained by the temperature. It's a lot, right? The remaining 1 minus 0.985 would be could be attributed to just pure randomness, or it could be due to other factors that we failed to consider. But it's already significant. The temperature is almost all what we need in order to explain the variation in the prices of ice cream. You don't need any other else, right? That's why you observe that ice cream is a seasonal product. You observe that during summer, when the temperature is high, the sales of ice cream goes high, right? It's seasonal. It's a seasonal product. It's the same thing um, as with decoration materials during, like for example, holiday decoration for Christmas. You would observe that during this months where you have like n months from Christmas, the sales of decoration materials increases, right? So you don't need any other things for that. It's seasonal, so you just need to take advantage through other things like giving discounts or giving other promotional things so that you could increase the sale. But you don't need any other things to really understand how what drives the sales. Okay, it's very easy for a seasonal product, particularly in understanding the price fluctuations. But it's not always the case. There are times that you would observe a seasonal product would suddenly um, um, you would observe that the sales suddenly gets high for some unknown reasons, and after further investigation, you would identify that Mr. Beast bought all of the all of the like all of the sales, something like that. Those are called outliers, by the way. So moving forward, um, Okay, let me see what we have in it here. Mm, Let me. Where's the p-value here? It doesn't show the p-value. I forgot to show the p-value here. Let's add the p-value. P-value. P-value would be, what was that? P-value. Hmm. Uh-huh. It's showing here, but it's being read as slope. Oh, I see it. I see the issue now. There we go. So the p-value is something that we also need here. That I failed to include. Oh, it doesn't make sense to have a p-value of 1.24. Uh, Let me see. We have a summary for Lingress. Sci-fi stats, Lingress summary. I need a documentation for this one. And we need the Lingress. Was it in stats model? Sci-fi stats. Lingress. I need the Lingress. Where is it? Lingress. Sci-fi stats. Uh, yeah, let's use this one. Let's repackage this. I don't think that Lingress has a summary function. So let's try to edit this. It's just easy. So we need the data for this too. Will be numpy yes np import stats models that api ssm import stats models that formula and um, my model is equal to smf dot tools. There we go. This is what I need. df is not defined, so let's define a df right here. df would be pd.dataframe. Why is it? Oh gosh, I forgot to import pandas. Okay. There we go. So where's the p-value? P-value, p-value. There we go. I wonder where this value came from. Or is it maybe it's a exponential, negative exponential value. Let me zoom out. I have the, oh, that's it. Okay. Do you see it, Grace? It's on a negative exponential value. P value is 0 to 1, right? It can be negative, it can go over 1. So this value is a negative exponent. So it means there are
There is
8 zeros before this 2. It's, there are 8 zeros, not before that, but after this. So after this decimal point, it would be um, 7 zeros after 1. So you move it 8 places to the left. So it's a very small value. Now we have validated it using this OLS regression result. That is a very low value, 0.000. So again, just like what I told you earlier, there are so many ways to do regression analysis using Python. This is one way. Using a different thing. So any questions with this, Grace?
So like um what are we concluding from those calculated values? We have a
Yeah.
R squared that there is correlation,
Hmm.
and then the linear, what do we get from the linear regression model?
Regression. Yeah, yeah. So
Well, what
that's
can
a
we
great
say from
question.
that?
Yeah,
Yeah.
yeah. We have identified that there is a positive impact, and we were able to quantify that. That's around $7 per every unit increase in the temperature for a degree increase in degrees Celsius. Aside from that, the p-value tells us if that effect did happen by chance alone. So that's what we're after with the p-value. Can we say that it is statistically significant? You can answer that by looking into the p-value, because it could possibly happen that there's an impact, but it could be attributed to purely chance alone. And in reality, if you look into the population distribution, it's not different from 0. So that's actually the null hypothesis of a regression analysis. So what is the HO of that? That is the population. The population has no relationship. Oh, no, no, no. Sorry for that. In the population, there's no relationship really between ice cream sales and temperature, meaning the effect is really indifferent from 0. So that is, we can say that the beta, okay, people write it this way, even in textbooks. Beta is equal to 0, and your alternative is beta is not equal to 0. That beta refers to the effect. Does it make sense, or did I confuse you with that?
I'm lost with that.
Okay, okay. Let me do a recap. Um, I'll use this to show you the generic formula for regression analysis. Okay, so the generic formula of a regression analysis is this, Grace, which is basically the equation of the line. So you have this beta 1 right here as the slope coefficient, which is basically also the effect of your x variable to your y variable for every unit in your x. Unit increase or decrease. Okay? This beta null is your intercept. So going back here in our model, this 7.0075 is the slope coefficient. And this 13.844 is the intercept. Now, we are inferring, okay, we are applying inferential statistics because we are hypothesizing here. We are inferring that if we look into the entirety of the population, okay, that is what I refer to as a population distribution. If we take into consider that, okay, the distribution of the population, is this beta equal or indifferent from 0 or not? Because if there's no evidence to say that it is different from 0, then we cannot reject HO. that this value happened due to sampling error, right? The reason why you observe an effect is because of the sampling. Okay, you can attribute that the sampling error, but if you look into the population as a whole, this value is actually zero. That's what we do when we set up hypothesis. We are inferring about the population, not on the sample, because if you repeat the sampling process here, these values would change, right? These values would change. But since we know the underlying distribution of the ice cream sales and the temperature, we can infer, okay, knowing that, is it significantly different from zero or not? And how do we do that? We look into the p-value, because this p-value tells us, okay, since it is a very small value, 0.00, we do have sufficient evidence to say that the observed effect is statistically significant. It's not just a fluke, okay? It's just by accident that we observe that value. So it also tells us in a different perspective that what is the probability, okay, under the assumption that this effect is zero, okay, we can observe a test statistic as extreme as this. It's 0.0000. It's very low. So if that's the case, then we can say, okay, HO must not be true. Did I confuse you with that? I hope I use the correct words. Or should I explain it a bit more slowly?
Just repeat that one more time. So with low p-value,
Okay,
we will reject the H naught.
yes.
Is that what you
And why?
said?
Can you tell me why?
The H naught is saying that there is no correlation, but we know that with the p-value closer to zero is how I would
Yes,
say it,
yes.
that that there is a very strong so
Evidence.
would I say association or correlation between the two value sets?
Yeah, correlation is good.
Correlation, yeah.
Yeah. Okay, so let me repeat one more time. Okay.
Yeah.
Um. So good. Let's forget this for now. Let's forget this p-value and so on. We know this equation model resulted from our data, right? We modeled it. We identified that there's this effect, there's this intercept, and so on. And we have said that, okay, since the effect is positive, we are saying that there's a positive correlation between the two. And also, earlier, we have computed for the correlation coefficient, and we have identified a positive correlation coefficient. Now, here's the thing. In simple linear regression, when I say simple, you only have one x and one y. The correlation coefficient almost tells you everything. Okay? Almost tells you everything. The 0.99 that we got from the correlation coefficient gives you an idea that there's a strong positive relationship between the two. What it doesn't tell you is this. What could be the effect of every unit increase or decrease in the Celsius to your ice cream sales? It doesn't tell you that, right? But it already
Can you
gives you a
say that?
hint.
Can you say that again?
Okay.
Just
What
it
the
doesn't tell you
correlation
what
coefficient,
each change in unit. Is that what you're saying? What each change in
sorry,
unit?
Grace, can you say it again?
You're saying that the coefficient cannot tell you what each change in unit will do to
Exactly.
the output?
Yes. It doesn't tell you that. That's the difference between a linear regression and just a merely correlation. With regression, you can understand, you can quantify the effect, the impact of every unit change in your X variable. That's something that you cannot do with just merely correlation. That's why correlation is the first step before you do regression. With correlation, you just have to see whether there is linear relationship, either positive or negative. After that, you need to understand more. How can the changes of my x variable affect my y variable? It's a deeper understanding, okay, of the interaction between your x and your y. So that's it. You have identified it. Now the third step is you would ask yourself, does this happen by chance alone? Is it just a fluke, or can we just associate it to the sampling error? Because it could possibly be that you have observed an effect because you just happen to choose this particular measurement of temperature and sales through the sampling, okay? Through the sampling. Now, if you want to say in general, infer that wherever you go, wherever you measure, it would still be that there's a positive effect in every unit increase in the temperature measured in Celsius to the sales in the ice cream, wherever it would be. It could be in America, it could be in Europe, it could be in Asia. Okay, of course there would be variability in the actual measurement, but it would still be positive, and it would still be near a certain range. That range is what we call um, interval estimate. We will be talking about that later. What we're doing right now is called a point estimate. Okay, a single value for the estimation of the parameter. So, in order for us to answer that, we will be doing hypothesis testing. We will be defining this hypothesis, two hypotheses then, HO and HA. We are arguing here that this beta, why did we use beta? Why don't we use um why don't we use other term? We can actually use it like uh any other word that you prefer, but it must be clear that what you are hypothesizing here is with regards to the population distribution, not only on the sample. Because in statistics, what we're actually doing is this in the inferential one. Okay. What we're doing right here is there's a bigger population, right? There's a bigger collection of things. Sometimes it's impossible, well, oftentimes it's impossible for us to get all the units of that population. So we resort to sampling. We get every beat of it, right? Not every, but some, just similar to doing blood samples. We mimic the characteristic of the population in the form of samples. So this is like a smaller version of it. Of course, there's some degree of variability. There's some degree of a difference between the two. But we are sure that as your sample size increases, you're actually approaching this. So that's basically the theory of convergence. As you increase your sample size, the distribution of your sample would approach the distribution of the population. Now, if we measure the characteristic of the sample, that is called a statistic. If there's a way for us to measure the characteristic of the population, that's called a parameter. So this parameter is what we estimate with the statistic. So this is a statistic, okay? This is a statistic, okay? We can think of it as the X bar in here. And this beta right here is the mu. Something that we don't know, but we are guided by theory that if we follow a certain principle, such as sufficiency of sample size and random selection, this sample statistic is near to the population parameter. Are you still following, Grace?
Yeah. Yeah. This part,
A bit
yeah.
off. So uh, let me do it in Excel. Let me give you a bit of maybe a practical example for this. I think what I'm drawing here is a bit too technical. So let's try it with Excel. We will discussing the nuances, the important aspects of this in week number 3 of statistics. But it so happened that I introduced you this method, and I want you to have a deeper understanding of that. So suppose we have a population here. Let's make it uh let's make it small, maybe 30 to 80, and then let's have this. Okay, and let's compute. Um, I'll copy it so that it won't change. Then paste values. So let's compute for the average. So this is say population mean. We get the average of that. So it's 54.25. Now let's do a random sampling. Maybe we'll get six units to form our sample. So that would be n. So let's take 57. Let's take 59. I'm just doing it randomly. 45, 50, 53, 38, and lastly 72. So we have 1, 2, 3, 4, 5, 6. Now we compute for the population, for the sample mean. So this is one version of the sample. We compute it. Okay. So as you can see, the sample mean is near towards the population mean. If we try to create a different version of that, we would observe that it's not really different at all. So this is the principle of statistics. Instead of getting every member of the population, we're actually studying the sample because it's more efficient, cost effective, and it gives us a good estimate of this parameter that we are trying to understand. So let's do sampling with replacement. There's a chance that I'll get um, another set of samples. So if we take the average again, we'll be sure that it would still be near this. Okay, so as you can see, these are the samples, and while it's not exactly equal to the population mean, it's still near. So understanding this would give us a hint about this. So that's what we're trying to do here. If we go back to this regression value, we're not hypothesizing that it is equal to any particular value. We're just hypothesizing that it must not be equal to 0. It could be 1, it could be any other thing, but we are saying here that it must not be equal to 0. Okay, so the interval estimate would be something like positive 0.001, and something could be crazy 18. But the thing is, 0 must not be included in the range of estimates. That's what we're trying to hypothesize here and trying to look for support through the p-value. If we say, okay, the p-value that we computed for this model, particularly for this effect, is less than 0.05, or cut off, then we can argue that there's enough evidence to reject this null hypothesis. It must not be equal to 0. because the p-value is very low. Again, the p-value is what is the probability under the null hypothesis, okay, under the assumption that the null hypothesis is true, that you observe an effect as extreme as this, and it's very low. So if that's very low, then you have to reject it. But for example, you observe a p-value such as this. What are the chances that you observe a test statistic such as if the null hypothesis is 0, 67% or 0.67? It's very high, right? Try to go back to our example of tossing a coin. If you said that the coin is fair and you observe that 900 times a head appeared, then can you still conclude that that coin is fair? What is the probability of observing that statistic if the coin is fair? Must be very low, right? But if you have like a result of 700 and 500, there must be a good chance that you can observe that even if the coin is fair. So similar to here, is there a good chance that you would observe this statistic if it's equal to 0? If it's 67, then yes. So we cannot reject it. But we cannot say that it's totally equal to 0, because there are other things that we can do in order to to make it more conclusive if this is the case. What are the things that we can do? We can increase the sample size. If we increase the sample size, we would have a better look into, okay, if the p-value is still high, if I increase the sample size substantially, then it must be a conclusive evidence that the effect could be just to purely chance alone. We cannot recommend that, okay, during hot seasons, the ice cream prices would or sales would be higher. Okay, does it make sense, Grace? Am I still making any sense?
Yes, but like feels very fragile, but I think we're still making sense.
Okay, yeah. I think it would be better if we have more examples. So more examples would. Okay. So you will get this more as we have more discussion, more examples. So don't worry. Okay. Of course, statistics is one of the most difficult subjects, so it's totally understandable that yeah, there would be this sort of confusion during the first time a concept is being introduced, and it's perfectly fine. So um, moving forward, I want to introduce to you another concept. Um, okay, independent t-test. So this is another method that you can do to your numerical data. Okay, and this is typically what's being used in A/B testing, especially if you just have like A and B options. Because if you have another option C, then we have analysis of variance for that. We will be discussing the differences between t-test and analysis of variance as we proceed along. So independent t-test is this. It is a statistical test that we use in order to compare means or averages. Suppose that you have two products or you have two versions of your product, version A and version B. Now, you want to have a concrete data-based evidence that one is better than the other. You can use t-test for that. Okay. I'll be switching back to Excel so that we have a good visual of what will happen. So suppose we have this products. Okay, I'll be using the same values here. So this is product A and this is product B. And just say that the numbers that you are seeing are count of buys or count of sales. So just count 1, 0, 1, 2, 3, 4, 5, 6, and so on. So count of sales. So for product A, maybe on day one we can say no, not days. Maybe site A, site B, site C, and so on. Because there's this another assumption of that's called independence that we have also need to satisfy. Um, just just do it dot dot dot. So we want to compare. We want to have a database evidence that one product is better than the other. Okay, in terms of the number of sales, we can use t-test for that. So basically, what we're doing with t-test is we're getting the means and standard deviation between the groups. So the formula is this. So the t statistic, just apologies for the noise. Okay, I may just want to use Wikipedia again here because I'm not too good writing formula using the mouse. So let me use this discussion. By the way, this is William Gosset. Mm, there we go. This one. There are different variations about t-test, but let me just focus on this example that I have. So basically, the ingredients that you need for the independent sample t-test, the one that you want to compare the two products, which one is better, is the mean of the first group, which corresponds to your x bar right here, the mean of the second group, and their pooled variance. So this SP, this figure at the bottom could be written this way. So this could be x bar 1 minus x bar 2, and just like that, I'm forced to write. Okay, so that would be square root of S1 over N1 times square root of, was it times? Let me just verify. Maybe my memory serves me wrong. Let me see. Let me just verify before I do a discussion. I feel that something's wrong with my formula, particularly the denominator. The numerator is on point. I should be a plus. Should be a plus, but it's good. Okay. So there are three ingredients that you need in order to run this. Of course, again, you won't be doing it manually. The reason why I'm showing you this is because I want you to understand how the computer analyzes it, how the libraries are doing the computation. Because I believe that it's not proper just to give you the steps in how to run it in Python. I believe that it's also well, it's more important that you know what's going on under the hood. So the ingredients that you need here would be the means for each group, the standard deviations, and then the sample sizes. Okay, so let's do that. If we go back to Excel, what we can do first is to complete that. So we have n1 x bar 1, right? X bar 1, s1, n1. Just complete those three for both the groups. So this would be 2 instead to have a proper identification for each of the groups. So this is just easy, right? Get the average, get the average for that, and then for the standard deviation STDS, we're using the formula for the sample. Do the same thing here. Okay. And then both are just 6. Once you have that, okay, you can plug it in to the formula so that you can generate a t statistic. Okay, a t statistic, and that t statistic would refer to the t distribution, the one that you saw earlier. So the t distribution was originally, I would say, discovered. Okay, I would not say invented, because I believe the t distribution is innate in nature, and we're just discovering them. Okay, there's different distributions. So the one, okay, I don't agree with the developed. Okay, the one who discovered t distribution and eventually use it in practice was William S. Gosset. Okay, so whenever you see the term student, the student refers to William Gosset. Now the t distribution looks like this. uh, these are not t distributions. T distribution looks like a normal distribution. In people call it a normal distribution for smaller sample sizes, because it was the original intention of that. How can we approximate using the same process as what we do with normal distribution, but for a smaller sample size? So this is what it looks like. As you can see, it's symmetric. Okay, it's bell shaped. But compared to a normal distribution, it's more thick. The tails are shorter as compared to a normal distribution. So if you do integral calculus here, if you compute for the area under the curve of this probability density function, it would still be equal to 1. So a valid probability distribution. So every degree of freedom, that's the parameter of a student distribution, would change the pickedness of the student t distribution. So it looks like this. Okay, it looks like a normal distribution. Now going back here, so as you can see, the t statistic could be either positive or negative. In fact, this is asymptotic. It goes to the limit is positive infinity and negative infinity. Okay, it's asymptotic. It doesn't touch the um well, of course, infinity is uh, going back here. So we're expecting the t value could be negative or positive. Okay, so I'll not be showing you that let me show you. Okay. So this minus this. Let's do the computation. Minus this, and then we divide by square root of this divided by that minus this divided by that. So let me verify if I have the correct one. I'm just applying the formula that you have seen earlier. This would give us the t statistic. Uh-huh. What am I missing here? E29 minus H29 squared, E30. Apologies for the noise. There's an ongoing construction here. So the problem earlier was the plus. It's a very low value. It's a 0.000 something. So this t statistic would give you a probability. Apologies for the noise again. Here's the thing. This statistics that we're computing, chi-square, t statistic, v statistic for the normal, f statistic, all of the different statistics. The main reason why we are computing them is for the probability values. So this t that is equal to 0 has a corresponding probability. And I guess that it is equal to 0.5. So in order for us to know, we can use t-table. This is the classical way of doing this. There's an associated table for every value or certain value of t statistic and its corresponding probability. Of course, I will not be asking you to do this. It would be crazy to have you compute for this or look for this way. I just want you to be aware about the process. So we are doing 2 for now, 0.05, and degree of freedom is 6. Minus 1. Let me see. 0.5. 0.5. 0.000. Mm, the associated p-value here is 1. And let me discuss why. So from this table, we have a degrees of freedom of basically 6 equal to Rn, number of observations. So we have equivalent for the two tails 1. So that p-value is very high. And why is it so? Because remember, these values are taken from just the same distribution. And looking at the values of the statistics, they are the same. And we also know that the parameter actually, the population mean is almost equivalent to that. So what this tells us is the two groups are the same. So that is, we have to define our HO, HA. So our HO here is that means are the
Sorry,
same.
Jeff.
Yep.
The sound was cutting off. So you were saying, so that tells us that the two groups are what?
The same.
The same.
Basically.
Okay.
Comparable. Why is that so? Again, the reason why we can tell is because we just created a population here and just extracted by random sampling each part of these two groups until we get 6 observations for each. But look at the x bar 1 and x bar 2. Remember, the numerator of the formula is the difference between the two. So 0 divided by anything is just 0, right? 0, well, aside from another 0, of course, that would be undefined. So 0 divided by any number, right? Any positive number, or, that would be 0. Even a negative one, it would result to 0. So it means that, okay, that equivalent to a p-value of 1. I think there's a as you can see, there's a shortcut. There are tons of tricks in here. So either you use the table, that's good for you if you know, or use technology, right? It's always more efficient. So the same way, we got the same thing, right? Or two different ways we got the same thing, p-value of 1. And what is p-value again? If the p-value is low, the HO must go. But the p-value here is very large. In fact, it's perfect, 1. So that's a strong evidence in favor of the null hypothesis. And what is the null hypothesis again? Means are the same. So the two groups are comparable, meaning there's no evidence for us to say that one group is better than the other, or one product is better than the other. That is independent sample t-test. And a way to visualize it, I prepared something in Python. I hope I'm not making you dizzy by switching back and forth to different platforms. Um, I prepared something that would allow you to visualize what's happening here. So imagine these are the sampling distributions of the two groups. The two groups are comparable with each other. The density plots would overlap each other. It means that they are comparable. They have the same means. Okay, same population means. Now, if we change the parameters here, like for the sample mean, if I make it very high for the other one, don't worry, I'll explain line by line this thing. Notice that there would be a shift. There would be a shift. As the difference between the mean gets larger, there would be a shift to the overlapping of the distribution. And the moment that the overlap is very small, then it gives us evidence to say that they are different from each other. And there are two parameters here, the scale and the location. The scale means the standard deviation, the spread, and the location is the center. That's the mean. So uh let's make it different so that we observe a non-over okay, this one. Now notice the area that corresponds to the similarity between the two groups is now very small. Okay, that corresponds to the p-value. So if you apply integral calculus and again compute the area corresponding here, that would give you the p-value. And that is very small. It's probably less than 0.001. And that would tell us, okay, the two groups are different. We're inferring not for the sample, but with our actual probability distributions, actual population probability distributions, okay? So we can generalize that even if you repeat the sampling process 100 times, 95% of the time you would observe a similar result. Okay, that's how confident we are if we have a 95% confidence level here. And the confidence level actually changes the critical values for each of the statistic. We will be discussing that in the sampling distribution part. But this is what I would want to show you in this part, in this session, is how to visualize, how to think of when you encounter t-test. Okay? Now, for the different flavors of t-test, we have the independent sample t-test, which is the one that we discussed. You are comparing two groups. There is this dependent t-test. Dependent is, it is the same set of samples, but across time. So you typically do that in experiments, in a longitudinal study. Imagine that you want to see the efficacy of a diet program. You measure the initial weight of the participants, and after a certain duration, say 1 month, you then observe their final weight. And you want to see if there's significant difference, if the final weight is much less as compared to the initial weight. It would give you an evidence to say that your diet program is indeed efficient, or I should say effective. Okay, so that's dependent sample t-test. There is another flavor of t-test called one sample t-test, in which you are trying to compare the means of um, a certain group to a hypothesized value. For example, I would hypothesize that the average height of Americans would be around 175 for males. Now, how can I say that guess or hypothesis is realistic? Okay, how can I say that? I will be taking samples from the population of male Americans and then um, generate a t statistic by subtracting the sample mean that I will get to that hypothesized value, and then observe the t statistic. Okay, so those are the different flavors of t-test that you would see if you browse t-test. Okay, and I'll be giving an example for each of that. Don't worry. So if you go to Wikipedia, you would see those different versions. You have a one sample, you have a two sample. The two sample has two sections, independent and paired. Paired is also called dependent samples. Okay, dependent sample t-test. And the assumptions, we'll be discussing them in the third or fourth week of statistics. But now I just want you to have an overview of this method and what's going on when you do A/B testing. A/B testing is just comparing groups, group A and group B. Okay, if you have two versions of your website and your boss wants to know and what wants you to identify which is better, is it website A or website B? As a data analyst or the data scientist, you need to apply this method. Okay, you would be needing to find evidence. For example, it could be a measure of clicks or duration of stay in the respective websites. If you see that the parameters are significantly better, okay, in one version as compared to the other, then you can objectively say, okay, that version of the website is better than the other. Do you follow, Grace? Again, I'm sorry about the noise.
Yeah, yeah.
Okay. So I think this is a dense discussion. You will have no lab tomorrow. You will not have any session on Saturday. But I'll be giving you reading assignments. I don't want to be difficult on the group, but this is just this reading assignment is designed, or the intention of it is just for you to have more background. It's for you ultimately. It will not be a requirement, but I hope you read it. I hope in the future, even in the future, you use it as a guide and some links that you can watch for some further explanation about these things. again for your own I should say betterment, for better understanding of the topics. The Python aspect is just easy. We have tools, but again, we should have clear understanding of the methods first before we transition to that. And that's what we have for today's session. Uh, you're the only one here, Grace. So I think I should. Well, I leave it to John on what you will do during the lab. Um, but I hope you enjoy the long weekend and your break tomorrow. Thank you very much, Kate. I highly appreciate you staying, and see you next week.
Yes.
Okay.
I'll see you next
Yep.
Monday.
Yep.
Take
Thank you very
care.
much.
Hey, John.
Hi, Grace.
What are we
How
doing?
was it? How was it? How was the discussion today?
Uh,
What is the topic that
okay.
you have
So
covered
I
today?
I had a hard time paying attention because then he'd go over like, well, see if we have okay, two means is when we take two samples, and then it feel like too easy, and so there goes my mind wandering off, and then he next thing he's saying something, and I said, what wait, what the heck is correlation versus linear regression versus p-value? And I was like, oh my gosh, I cannot reiterate what he just said. So it's
Okay.
like I was getting it, but I wasn't getting it. I think I
That's
just need to rewatch maybe or
wait,
like supplement it with something, right?
wait. I suggest you rewatch the videos of Sir Jeff multiple times. That's the thing that I can suggest. That's the
Yeah.
same the reason why I'm laughing is not to make fun that you find it hard. That's the reason why I'm that it's because that's the same reaction that I had when I had Sir Jeff as my instructor in statistics. Yes,
Yeah.
exactly. Like, okay, I think I have the file here. Let me show something to you. And I plan to also share it to the class, but I will I will get permission first to Sir Jeff. This one is the midterm exam that I submitted on Sir Jeff when I was second year. And that the name of our subject is survey analysis. Survey analysis. Analysis. The name of the subject is survey analysis. And I think this one, midterm exam. So I was second year during this time. And the deadline of this midterm exam is only 1 day. Do you in that? Do you see how many pages I I have in this?
Is it chat?
I it is there are wait. I'm not showing I'm not sharing my screen. Sorry
Oh,
for
okay.
that. So wait, where is that? This is the midterm exam of our class 2 years ago. That
Mm-hmm.
time I was second year. The instructor is Sir Jeff. The name of the subject is survey analysis. And the term exam just consists of three parts: reflection, concepts, and creation. So in that time, we only had 6 meetings with Sir Jeff. And at the first part, he said that provide a detailed discussion of what you have learned of lectures 1 to 6. So lecture 1, I provided everything that we
Oh,
learned about that meeting. Like it is only lecture 1. We have lectures 1 to 6.
oh my gosh. Assignment was like to be a scribe.
Wait. Hold on. The other instructor is calling me. So
Mm-hmm.
for now,
Okay.
let's you can read this part. So hold on for a minute.
Hasiba, he's in a call with the other teacher right now for a moment.
Okay, thanks for letting me know.
Okay, so it's it's very hard. So I guess it's okay if I will share this to the group. I will send it on the Discord. IDA April. April downloads. And to let us see pa now, this is my midterm examinations with Sir Jeff 2 years ago, the time that we have a discussion the last time. Let me share my screen. And I think this will be very helpful because there is a part here, like the section B, that discuss the p-value, what's the meaning of hypothesis, what's the meaning of hypothesis testing. Actually, I created an activity on the canvas that is all about those stuff. So let me post it. And since I shared the file to you, what I can suggest is first try to answer this file at on your own, like try to complete it on your try to complete it on your own first before you read this file that I shared on the canvas. Wait. But the thing that wait. The thing that I'm saying earlier to Grace is um this file of 10 pages, we completed it within 1 day. He gave it to us at like 7 a.m. of this day, and the submission is up until 11:59 p.m. of that day also. And this is as entry type. So as you can see, all of this we wrote it. So I shared this file to you, and you should be able to access it on the Discord. So on the discussion earlier, Grace, what is the part of the discussion that you find very confusing? Let's try to simplify things.
It's not so much that it was confusing,
Mm,
but more so just like, okay, what do I do with this? I think like in trying
mm,
to explain the formulas, which is necessary because then it's like, I don't understand why do we want to like celebrate a big number here, but for these it has to be a small decimal number. Like you want to understand where it's coming from too, but then
like
yeah, because we're not like statistics major,
mm,
and so we need to know like enough statistics though in order to do the job. So I just felt a little bit like, okay, then now let's apply this to more practical and like
the
how can we
practical part.
explain this? Yeah, as if we're the
Mm,
analyst presenting, we did the necessary computing of the numbers and this and the separating and the sample.
and
And then now I'm explaining everything with my graphs and my p-values because I put in the Python formulas. But then it's like now, what do I say with this? I think
like
we at least need to practice that or something.
like the interpretation part and the reporting part after you perform all of those calculations.
Yeah.
So so with that, I think we need a data set that's
Exactly. Like let's do a case
mm,
study, something small. Let's find the p-value and linear regression and all that stuff. And we will practice together. Like, how would you present this to your client?
oh yes. But for now, let me have here some data sets. I think it's okay if I will present these things. If I will present these things because it doesn't contain any information about the individuals. So up here, this is just 8 page. This is one of the projects that I performed during the time that I was still learning how to do statistics. So what I'm doing is I'm searching for people who are conducting their research, and then I ask them if I can provide them a statistical service, something like. And at the beginning, I do it for free, and the way I did it is on this structure. So you can get here a way like to a strategy to present your data. So your your this data set looks like this. Recorder. I think this one. I'm using SPSS that time, but this is totally performable using the Python. But for now, I will show you the structure of the data that we have, where that output came from. Oh no, not this one. Don't want that file. Okay, this one. Please neglect the names. So the data set that we have is consists of the sex, the age, and some questions. These questions have different names. And but the point is there is age, there is also the sex, and what are the other things here? This is about the survey. And these are just group of questions. So think of it that it is a Likert scale that is answerable by numbers 1 to 5. And those numbers 1 to 5 has a meaning like agree moderately, agree um, very much, disagree very much, depending on the number that they will put there. So analyzing this, I come up with this state with this five. Let me find that. Oh, there's too many tabs. Oh, this one. So the first parts of the analysis, I just presented the descriptive statistics. As you can see, I presented the mean, the median, the mode, the standard deviation, the minimum as well as the maximum. So in Python, we know how can we perform this, and that is by using the that describe if and it will automatically be applied on the numerical values. So the that describe is very useful if you want to describe the numerical data. It is also useful if you want to describe somehow the categorical data, and that is the sex and let's say the educational background. Like it will present the frequency as well as the percentage on your data set and somehow report it in the way that it is straightforward. The average age of your respondents is 21.52 with the standard deviation of 2.053, meaning on average, the age of the respondents are 2 years away from the mean. So it could be 19 years old or they could be 23 years old. The range are playing around that value. And somehow these sentences came from these values. Like I presented who is the highest, who is the lowest, what is the mode, something like that. I just storytell it. What are the values that I found here? Okay, let us scroll a little bit. The next one that I described is the the sex, and we saw that out of the 50 respondents, we have 16 males, we have 34 females. So you can use bar graph there or pie charts to present, somehow visualize how much many the female over the male in your data set. So the demographics, it is more on demographics are applied more on the descriptives is applied more on the demographics if you are talking about people. So that's the case. If you are talking about the product, you can apply it by the categories, by its color or some grouping. And the way we report it is as simple as this. The respondents consist of 16 males and 34 females. Like, even if that is very obvious, you still need to somehow create a paragraph for that or a sentence. And we have here the test of normality. As I told you earlier, I think yesterday, we have a proper test of tests if the data is normally distributed. One of the tests is the Kolmogorov-Smirnov test. And these are the p-values. What do you remember about the p-values? We reject null when the p-value is less than 0.05, right?
Mm-hmm.
Do you remember that convention that we have yesterday? Reject null
Yeah.
if
But
the
this, where's
p-value.
the P here? Is AP mean the P?
No. This is your variable. Your variable is the age. These are the variables. These are, you can think of it as your columns. And you are asking if that columns are normally distributed. So let's say this age. Is your age normally distributed? Okay. So the null hypothesis there is it is normally distributed. The alternative is it is not normally distributed. So the null hypothesis is it is normally distributed, meaning the way, okay, let me edit this. The way age is distributed is normal or is the same as the normal distribution. Like there are so low number of people who have a very high age and a very low age. Most of them are at the center and it looks like bell shape. So you are asking what's the shape of the distribution? Is it the same as the normal distribution or no? So using the p-value, this part representing the age is less than 0.05, meaning the Jack null hypothesis. The Jack null meaning the age is not normally distributed. It does not follow normal distribution. So here we just reported it based on the results.
Drawn to that
Age
right
is
there,
not normally
reject now.
distributed. Okay.
Can you
It's
add on there the standard? So since P is below
okay.
0.05,
Okay, sure.
is that's correct, right?
Yes.
Below 0.05, we reject. No.
So describing the age, since the p value corresponds to it is it under the test of normality, there is 0.001 and it is less than 0.05. So at 95% level of confidence, it is not normally distributed. So something like that. AP mean is also not normally distributed because this is less than 0.05. This is distributed because it is greater than 0.05. So we have a way to test the way our data is distributed. One way is Kolmogorov's method. Right? So this, if you know the problem, like I want to determine if the data is normally distributed, you can search online tests of normality and what is the proper thing to be applied. So here we have two well-known tests of normality. One is called Kolmogorov-Smirnov test, one is Shapiro-Wilk. The one that I used on this analysis is the Kolmogorov-Smirnov test. So now it will be followed. You can use ChatGPT or other search engines. So how to perform test of normality in Python, something like that. And then you have recommendations by using the plots and also by using the Kolmogorov-Smirnov test or Shapiro-Wilk. And the reporting is the same. If the p-value that you would get there is less than 0.05, therefore it is not normally distributed. Meaning you cannot apply parametric tests, are not applicable. Why? Because one of its assumptions is your data should be normally distributed. Okay? We have assumptions for parametric tests. And one of its assumptions is your data should be normally distributed. So let's go at the bottom and performing the chi-square tests. Chi-square test of association. We determine if the job satisfaction is related to the age. Right? We are interested in that. And we have seen that under the chi-square tests, you can get a p-value, which is this 0.47. And remember what is the null hypothesis for chi-square test. It is always the same. It is always the same. It's just that for every research, your variables are changing. You are dealing with another variable. So in chi-square test, you said that since this is greater than 0.05, meaning the null hypothesis is failed to be rejected. This means that there's no significant relationship between the sex as well as the job satisfaction. Okay, regardless of the sex of the person, it doesn't have any relationship. It doesn't explain whether the person is satisfied on the job or not. Okay? And that is because this is greater than 0.05. In case that, let's say this one is 0.03, 003, something like that. Since that thing is less than 0.05, so our conclusion now will be there is a significant relationship between sex and job satisfaction. But since that thing is greater than 0.05, it is 0.47. Therefore, there is no significant relationship. That is how we report our data. Like, since you are using Python, it is easy to display the value. Like, what is the p-value? What is the test statistic? Even automatically, the degree of freedom shows in other softwares. But after you calculated that, what's the meaning of that? It means this. That's why you should always practice this this part. Where is it? Do you still remember the step-by-step process that I showed you the last time? The step-by-step process of having a research problem. Where is it? I don't remember where did I put it. I can't find that step-by-step process. Maybe it's on the Google Colab.
Did you check your sheets on that Excel sheet?
Let me go back to that. What's happening? I'm not sure where did I put it.
Yeah, that's not it either.
Maybe it's on this. Okay, hold on.
Hey Grace, how are you, dear?
Okay, so I think I put it
Oh,
there.
sorry, Hasiba, I was on mute.
No problem. I will send you an email.
Okay, so maybe it's better if I will just type it again in more detail. So first, let me give you like the overview of the research process that we are doing. It is applicable for all the tests. Research process. First, you need to collect the data. No. First, define the problem.
Mm-hmm.
Okay. What do you want to do? Do you want to compare two things? Oh, wait. One thing to population. What we did, let's say, um, you created the product. Okay, you created a battery. Let's say you created a product that is a battery. And it lasts, let's say, for a week. In convention, like the normal designs of the battery, it lasts for only 5 days. So for the population, based on history, it lasts for 5 days only. But you claim that you created the product, your product, you said that it lasts for 7 or 8 days. So that is your claim. So your claim is your product is better. Something like that, right? So your problem is to prove that your product is better. So how can you prove that? In convention, like the standard, it is only 5 days. You test your batteries. You put 10 batteries you exhausted them, you recorded it. Part 1, part 2, part 3, part 4.
Okay, so scroll down.
And let's say part 10. And then record the days. And the days it lasts. Let's say this is the battery one lasts for 8 days, this is for 7 days, this one lasts for 6 days, this one for 9 days, and so on. Oops. Using your data, you are asking, is my battery better than the other batteries out there? Because normally, it lasts for 5 days. The normal average time is 5 days, but is your product better? So you have a problem that you are comparing your thing to the population. Or do you want to compare two things? Which is better? Product 1 versus product 2. Let's say you have two batteries. You created two batteries and you are asking which of them are better. You have the battery 1 and you have the battery 2 out here, and you will compare, is these two things different from each other? Or another way is, do you want to compare 3 or more things? So you should define the problem. Do you want comparison? You should. So are you? The point here is, are you comparing something? Comparing something. Or another set of problem is, are you interested in the relationship of things? Like, you can also extend it. The relationship of two things only. Like, relationship of your age as well as the salary, something like that. But the point is, the problem is here. Whether you are comparing something, you are asking for the relationship of something. So that's the problem. Given the problem, given that you have a clear problem, you should be able to generate hypotheses. Only two: null and alternative. So that's the second step. If you can successfully list the research process, you will find it easier to interpret the things after you calculated the statistics. Okay. Null and alternative is dependent on the nature of the problem. If you are comparing something, typically the null is product 1 doesn't have a difference with the product 2. And the alternative looks like 1, they don't have any difference. 2, product 1 is better than product 2. And the third scenario is product 2 is better than product 1. So you can write alternative hypothesis in different ways, but the null is all bit the same. There are no difference between the two. Or if you are comparing three things, there are no differences between these three things. Or if you are interested with a relationship, there are no relationship. There is no relationship between variable 1 and variable 2. So you need to generate hypothesis. Number 3, depending on the type of your problem and the hypothesis, select appropriate tests. Okay? And to select appropriate tests, these are the things that you need to consider. Data type. Is your data type numerical or is your data type not numerical? These are categorical. Numerical or categorical. Data type, because depending on the data type, you can get the test that you want. Like for example, the test that we have discussed, chi-square, is only applicable to categorical. So there are a lot of tests in statistics. I bet even if I grow old, I won't be able to use all of them because there are many tools out there. There are many statistical tests out there. So what we do is to narrow down our choices. So first ask what's the data type, and you can eliminate all of the tests that are designed for numbers, numerical types. So correlation and regression, linear regression, these are for numerical types. Now, number 4. So you selected a test. Now you should define level of confidence. So these are parts of the preliminaries, like before you perform the actual test. These are the things that you should have. So you have 95% and you have 90. These are the common things. 90%, 95%, and 99% level of confidence. Number 5, define rejection criteria. Rejection criteria looks like this. If your level of confidence is 90%, therefore reject null if the p-value that will be the output of your calculation is less than 0.1. If you are at 95%, reject null if the p-value is less than 5% or 0.05. If you have 99% level of confidence, then reject null if the p-value is less than 0.001. Is that clear up to this point? Is it clear up to this point? Because the number 6 is perform the actual test. You can choose your softwares. You can do it manually if you want.
Yes,
Manually
made sense so far.
or by software. And after you perform the test, especially if you are using software, you would get there given that you selected the appropriate tests, you follow the assumptions. By the way, performing the actual test requires what is happening in my Excel again. So this includes testing of assumptions. Like testing of assumptions or the checklists. If your data is not normally distributed, you can narrow down again your choices. Because let's say this one. Let's say you want to compare two things. If your data is normally distributed, you can use t-tests. Okay, let me put it here. If the data is normal, use t-test. If the data is not normal, use what's the test of that man with me you test. So maybe you're thinking, how can we know that this is the proper test? It should be based on the problem that you have. Like if you know the nature of your problem, let's say I want to compare two things. If you search online and if you read different uh, sources, what is the appropriate statistical tests if I want to compare two things? It will show you that you can use t-tests. But to use t-tests, your data should be normal. To use If your data is not normal, use this test. But to tell you the point of having these two tests, basically they are the same. They have the same purpose, and that purpose is to compare things. That is the purpose of these tests. But depending on the data that you have, that is the thin line separating them. It depends on the property of your data. So that are assumptions. This t-test is the parametric. This test is non-parametric. So imagine at any problem, you have choices. You have two containers that contains the choices. You have tests that are parametric and tests that are not parametric. Parametric tests is more elegant. Like the result there is strong compared to the other test, compared to the non-parametric test. However, the problem here is parametric test, there are assumptions that you need to check. That if those assumptions are not satisfied, you need to use the counterpart. But these two tests performs the same thing. So you can perform it manually or by software. And after you perform that, you would get the p value. And then the last part is decide. We only have two decisions. Is it either reject null or do not reject null? And it is clear here. If you are 95%, if you are working with the experiment with 95% level of confidence, by the way, this one is defined by the researcher. Like you will be the one who will define it. So depending on your defined level of confidence, you have the p-value. So going back to this, reject null, if the p-value is less than 0.05, and do not reject, this means that your p-value is greater than 0.05. Maybe you are thinking, what if it is equal to 0.05? Still reject null. So it's less than or equal to 0.05. And this is for 95% level of confidence. Remember that if you are working with an experiment with 90% level of confidence, your rejection should be at 0.1. Does that make sense? Is it clear up to this point? Hello? Grace and Hasiba? Let's say you're working with an experiment with 90% level of confidence. Reject null if the p-value is click this. The p-value is less than 0.01, but do not reject it if that is greater than 0.01. We also have the 99. So this is somehow the cheat sheet that you can use on algebra analysis. This is applicable on every analysis. Right? And then after that, after you have those p-values and after you decide, interpret, conclude, and interpret. Like, what is the meaning if we rejected the null hypothesis? So explain that decision in the way that it can be understood by normal, by typical people. So what's the meaning when now we rejected the null hypothesis? So what? So what's the meaning of that? So you can say that these two products, battery 1 and battery 2, has differences in their performance because we rejected their null hypothesis. Something like that. So I think it's better if I will transfer it to over to Python. So far, is this clear? Like for every analysis, this is the thing that you should be doing. Like first define the problem, generate hypothesis, select the test that is applicable for your problem, define the level of confidence, define the rejection criteria, and then perform the actual tests. Like as you can see on these steps, performing of the actual test is just part of the analysis. You have to do something before and after the actual test. Okay. And then you decide. And after you decide, you interpret. So that's the what I can say, the overview of the research process. Any questions on this, Grace and Asiba? Any thoughts or any additional information about this?
So I understand this part, but I really need an actual data that I could,
Mhm.
as Grace said, I could apply all these. So that time I would understand, I think.
Okay, okay. So
Yeah, like every time we will get surprised when we reach out to the exam. So this time I would like to like before exam or for my understanding, I would
okay,
like to
so
have something like that.
wait. Let me chat Sir Jeff now. Sir, to have data sets can be sir, do you have data sets that can be used to practice, let's say, chi-square test, because that is the thing that you have seen yesterday. So if I can get a data from Sir Jeff, I will send it maybe on the Discord or I will post it in the into the Canvas. And then for now, I will say what's the test that you should be performing on this data set. But in performing the test in that data set, this is the step-by-step process that you will follow. Define your problem, generate hypothesis, and so on. And you can improve it, like for example, under the performing of the actual tests, you should include here describing the data, something like that. Like the frequencies and the percentages, you can include that. So with that, I think um, it is more on theory, but I understand that you need an actual data set in order for this to understand and in order for the information to retain. By the way, I posted an activity on the canvas that
Yeah, can you please explain what should we do?
okay on the canvas, since we don't have any practices, we don't have any data sets yet. So for the meantime, I want you to provide a discussion, like in your own words, how do you understand the p-value? How do you understand the hypothesis? How do you understand hypothesis testing? Like in your own understanding, how can you define it? And we have some questions about the chi-square test. So first was what is the purpose of chi-square test of independence? So in your own words, answer that, like what data type can be used, what is the thing that what is the problem? Why do we need to apply test of independence? And like number two, true or false. And somehow I included here the word why. Like if you answered is true, um, even a simple explanation of why your answer is true is helpful. So this is part of the, like I am assessing whether what's your understanding of the concepts that we have so far, so that I can somehow adjust the way I show it to you. And its deadline is next week, but you can still access this file even if the deadline is done. Okay. Any questions?
Alrighty.
Yes,
And
please.
can you please send? Sorry. Okay.
What this file? Do you want me to
Yeah.
send this? Okay, sure.
Yeah, definitely that one.
I already sent. I already saved it. Like this file is the cheat sheet that I have. Like I am summarizing the things that I have learned on the statistics classes that I encountered. Statistics is so heavy. It's because if there's a lot of application, and it is understandable that some of the concepts will not sink in now. But I'm trying to explain it in the way that it is intuitive, so that it would have the understanding. So I sent it on the Discord, the research process, as well as this one, the PDF file of my midterm exam from Sergia. I suggest before you read it.
What is that? I think, I don't have connection, so.
That consists of some explanations, like what the p-value means, what hypothesis testing means, coding questions, and so on. Like some of the concepts there. But like this is just for you to have an additional readings.
Okay.
Okay. There's no thing that you need to perform at all. This is just an additional information that some of the questions here, some of the questions that was assigned on the Canvas, the answers can be extracted from this value, from this file. So what's the meaning of the p-value? So you might find this helpful on your statistics class. Okay, so I think that's it. Just a simple assignment that was assigned on the Canvas, and I'm asking Sir Jeff if we can get a file that you can apply the practicing of the analysis and that reading material that you can read, because there are a lot of days that we will not meet on this following meetings. By the way, are you informed that we don't have any classes on
Wow.
4th and 6th of July? Oh no, wait. You are not informed with that. Wait. 4th and 6th of July, there are no classes because of the
That will be
Independence Day.
tomorrow and
Yeah,
Saturday.
Saturday, yes. Tomorrow and Saturday. But is it okay, like, for example, I get a data set if I will post it on the Canvas or Discord, so that, like, if you want to practice, even if there's no classes, you can do practices. Like, where is it? Where is it?
Mm,
Where is that announcement? I think on the teaching assistant groups.
I suggest it
This
should be
one,
next week because
4th and
this
6th
is a
of July.
holiday and everyone has plan.
Okay, okay.
I
I'll
think
take
what
a note of
happened is
that.
Sherry posted it in general chats instead of our IDA. Or are you looking at it already?
This one, and I think this is also posted on the general chats of the students. But
Yes, she shared the one with like the yellow background with just a list of dates inside. Or I mean, I can check.
okay, 4th of July and 6th of July, we don't have any classes, so that's the reason why we'll see each other on Monday. So I guess that's it. Thank you for that, Grace and Hasiba. Let me know if you have any concerns on the Discord about the
Sure.
statistics.
There's a
So
lot of
thank
reading
Thank you
now.
so much.
You guys are.
That's amazing.
Ugh.
That's a lot of reading. But you are
Yeah.
not, this is just my material. Like, this might help you. You don't need to read everything because this is my output on exam. But you might find it interesting. It talks about all of the topics about survey analysis and also the values that you should be looking. So you can read it. You have a choice that do not read it, but it would be nice if you will read it. Okay. So with that, I think that's it. Thank you everyone and see you next week.
All right. Good
Thank you,
night.
John.
Thank you.
Have a good one.